Hi everyone and welcome to this video on the optimization problems, which are basically problems where we try to find a maximum or minimum value for a particular function. There's a couple of things that we need to sort of take into consideration when we're doing these problems. Now, usually when we differentiate at this stage, we only do so with one variable, and so we can actually end up with equations that have multiple variables in them, and we need to somehow find a link between them that we can use to, essentially turn it into a one variable problem. So I'm going to get into a couple of these today, and we'll just see how they go. So this first question is it's like the stereo, it's just the question. It's like one which you've probably actually encountered before if you've studied cubic equations. And yeah, we'll just have a look at how we can go about solving something like this. So a rectangular piece of metal measuring 28 centimeters by 18 centimeters is to have a square cut from each corner so it can be folded up to make a box. Find the maximum volume of the box. Okay, so first things first, I'm going to actually just draw a diagram for this and see if I can sort of visualize what's going on. So we have a rectangular piece of metal measuring 28 by 18, and it's going to have a square cut out of each corner. Now, it doesn't say anything about how big those squares are, but obviously they'll have to be the same size so that when it folds up, we'll actually make a box shape. And because I don't know what the length is, I'm going to call those lengths x and x. Okay, so what that means is that the amount that we have left over, so this distance from here to here, is essentially going to be 18 was what the whole side length was along here. We're cutting x off there and we're cutting x off there. So this bit is 18 minus 2x. And likewise for this part just here, so measuring from here to here, we had 28 along the full side length initially, but now we're removing 2x because we cut x off each side of it. So this part here is 28 minus 2x. So these are the dimensions of the box, and we can sort of write an equation now for the volume of this. So I'm going to say that the volume is equal to, now to do the volume of a rectangular prism, we do length times width times height. So the length of this one will be 28 minus 2x. The width of it will be 18 minus 2x. And the height, or when we fold up this part here, that's going to be the height of it. And so the height there is just x. And so now we have this expression for the volume, and I think it's pretty good from here. So the thing is that we want to maximize the volume, and we can see first off that this equation is all in terms of x, so that's fine. We have essentially one variable which we can work with. So what I'm going to do is I'm going to bring up the calculator here. And first things first, I'm just going to basically see what this is equal to. I'm going to expand it all out. So V equals, now if I go action, transformation, expand, and then I'll put in the 28 minus 2x, the 18 minus 2x, and the x. So 4x cubed minus 92x squared plus 504x. Okay, that seems pretty good. Now the thing that we also have to consider here is that there are some limitations on the value of x, and that's because, well, for example, this shortest side length here is 18. Okay, and so if that's 18, we're cutting x off each side, then we can't cut off any more than 9 from each side, because if we cut 9 off, then we end up cutting off the whole side. So and likewise, we can't cut off 0, because that just doesn't really make sense, and we wouldn't have a shape that we could actually fold up. So I'm going to just write these limitations off on the side. I know that 0 must be less than x, must be less than 9 centimeters. So, yeah, what I'm going to do now is I'm going to differentiate this, and we're going to find out what the x value is, which gives the maximum. So, next thing is to get that derivative dv dx, which in this case will be 12x squared minus 184x, and then plus 504. Now, the other thing that I'll say about these questions is that they tend to be fairly tricky. They won't necessarily work out nicely, and you'll usually have decimal places involved. So you have to be using your calculator to solve these kinds of questions. So I'm just going to do that here. Now, when we're looking for the maximum, we want the derivative to equal 0. So I should actually say let dv dx equals 0 for the stationary points. And that means 0 equals 12x squared minus 184x plus 504. Alright, so I am going to solve that now. So 0 equals 12x squared minus 184x plus 504. And then I'll just highlight that and go up to interactive equation solving for x. So that's alright. So x equals 3.57. X also equals 11.76. Let me just write these down. So x equals 3.57 and 11.76, I think it was. Yep. Okay. So the thing is that there are 2 stationary points here, and this is where the domain that I mentioned earlier becomes important, because we know that the x value can't be any more than 9, otherwise we would be cutting off that whole side of the shape. So the x equals 3.57 must be our answer. There is another way to sort of confirm this, and that's by knowing the shape of the graph. Now, if I look at the equation listed here, I can see that the number in front of the x cubed term is positive, which means it's a positive cubic, and a positive cubic graph has that kind of shape. So the smaller x value will give this maximum point, and the larger x value will give the minimum point. And remember, what we're looking for is a maximum volume. So now that I've got that x equals 3.57, what I'm going to do is I'm going to put that back into the equation. So sub into the volume equation. And if I bring up the calculator now, I'm going to have 4 times 3.57 cubed minus 92 times 3.57 squared plus 504 times 3.57. What have I done there? There we are. So 808.75. So the max volume equals 808.75 cubic centimeters. And yeah, I think that's sort of all there really is to this particular problem. Now, there is another way that we can see the answer to this, and that is by graphing the equation. So I've already written the equation just here. I'm just going to highlight that and drag it down here. I'll put a y in front of it. Oops. And I will graph it. Okay, so it doesn't look like much at the moment, but you can see that the maximum volume was 808. So I'm going to change my window. So the x max, I know that it can only really go up to 9. I'm going to make it go a little bit further anyway. I'm going to make it go up to 15. And make the minimum 0. The Y min I'll also make, I'll go negative, let's go negative 30 and we'll just see what happens there. And the maximum I'm going to make 900. Okay, so we can see it's really got this shape just here. And yeah, we're looking for the maximum value. So if I go analysis, gsolve, max, you can see it says x equals 3.57 and y equals 808.75. So we've just confirmed that we've got the right answer there. I might leave this video here and I'll pick up a couple of other examples in the next few. I'll see you for now.